Let's see what are graphs and their types. Graphs are typically represented as the set of nodes and set of edges. Nodes are sometimes also referred to as vertices. Here is an example with 5 different nodes and 8 different edges. Okay, so there are different ways of representing the graphs, and using adjacency matrices is one of them. Okay, and it is very easy and very straightforward. Okay, so here we have a graph with 5 different nodes, and whenever we have a graph with n different nodes, we are going to need a n cross n matrix to represent the graph. In this case, n is equal to 5. That is, we have 5 different nodes. So we are going to need a 5 cross 5 matrix, that is with 5 rows and 5 columns. Okay, it's very easy. So for any pair of nodes, if there is an edge, then we represent that record as 1. And if any pair of nodes, there is no edge, then we represent that as 0. Okay, let's consider an example. Let's consider node 1. Okay, so node 1 is connected to node 2, node 3, and also node 5. Okay, so if we observe the row 1, that is for node 1, so there is 1 for node 2, 3, and 5, because node 1 is connected to 2, 3, and 5. So we represent these 3 records with ones. And also we can see that node 1 is not connected to itself. There aren't any self loops in the graph. And also we see that node 1 is not connected to node 4. So under these 2 records, we put it as 0. Okay, so it is very straightforward. If there is an edge between 2 pair of nodes, we put it as 1. And if there is no edge between 2 pair of nodes, we put it as 0. Okay, but there is one problem with this notation. Okay, so here we have total 5 nodes. Okay, so what are the total possible number of edges in this graph? Let's consider the worst case. So what can be the worst case? If every node is connected to every other node, then how many edges do we get? Okay, let's say we have a graph with n different nodes. Okay, so if every node is connected to every other node, then we will be having n into n edges, which includes the self edges also. Okay, in this case, we have 5 different nodes. Okay, so with 5 different nodes, the maximum number of possible edges in this graph are 25, right? That is, if every node is connected to every other node, including the self loops, then the total number of possible edges are 25. So we are going to need 25 cells to represent this graph in worst case. That is, if every node is connected to every other node, we are going to need a 5 cross 5 matrix. Okay, so this is the worst case. That is, if every node is connected to every other node. But in real time, this is not the case. Very often we never see that every node is connected to every other node. It's always the case that some of the nodes are connected to some of the other nodes. Okay, even in this case, in this toy example, although the total number of possible edges are 25, but in this case, we only have 8 edges. Okay, similar to this, even in real world, we never see all the nodes connected to all the other nodes. We only see some of the nodes connected to some of the other nodes. Okay, so we never going to need all these records, that is all these 25 cells. Okay, we also call this representation as dense representation. Okay, dense representation. Okay, and there are some other ways to represent the graph, which comes under sparse representations. Okay, okay, in real world, we don't really need to represent this dense matrix, that is this dense edges. That is, we need to represent what is the value for every possible edge. But we know that there won't be the case that every node is connected to every other node. So it would be good to only represent the existing edges. So there are many sparse representations. So one of the representations uses linked lists. Okay. And also there is one way where we use reference arrays. Okay, reference arrays. So likewise, there are many other techniques, but remember that adjacency matrix is a dense representation. We have different methods to represent the graph in a sparse way. Okay. And triples is also one of the sparse representation. Okay. And most often you see these representations in graph neural network papers and blogs. So this is very simple. Okay. So under triples, we only represent the edges. Okay. It's very straightforward. Let's try to understand. So triples contain only three different values. Okay, only three different values. Okay, here the first value is the source node ID. The second value is the destination node ID. So from this graph, let's say if you wanted to represent this edge, okay, so we have a edge between 1 to 2, okay, where the source node ID is 1, the destination node ID is 2. So we represent this as a triplet, okay, that is with the source node ID and the destination node ID, and we represent the relation between these two nodes, okay. In this case, as it is a simple graph, we don't have multiple relations. Here we only have a single edge between 1 to 2. So for now, I'm just putting it as a like simple hyphen. But in real world, we represent what relation it is between node 1 and node 2. Okay. So likewise, we represent every edge as a triplet. Okay. With three values. Okay. That is source node ID, destination node ID, and the relation between these two nodes. Okay. So triples will contain how many records? The number of records in triples will be equivalent to the number of edges in the graph. But there is, one thing to note. So here we are considering the undirected graph. That is, we don't have any directions on the edges, right? We don't have any directions on the edges. This is an undirected graph. Okay. You can also assume the undirected graph as bidirectional graph. Okay. As a bidirectional graph. Okay. So whenever we represent a undirected graph using the adjacency matrix, typically we observe the symmetry. That is, if you observe this triangular matrix, that is the upper triangular matrix, okay, with the lower triangular matrix, you can see it's almost same, like it is exactly same. Okay, whatever values you have on the upper triangular matrix are exactly same as the values in the lower triangular matrix. We also call this as a symmetry. Okay, because the upper triangular matrix is exactly equivalent to the lower triangular matrix. And this happens in the case of undirected graphs, because we see that 1 and 2 are connected to each other. So when we are representing the edge from 1 to 2, that is from 1 to 2, we have it as 1. And also when we are representing from the node 2 point of view, that is 2 to 1, here also we have an edge, right? So the same edge is represented as 1 to 2 and also 2 to 1. Okay. That's why even in triples, we represented this edge. We represented this edge with one of the triplet, that is 1 to 2. And there is another triplet with 2 to 1, right? So this is the case of undirected edges. But we have different other types of graphs. So we can also have a directed graph. Okay. So just to give you an example, let's consider the social network. Okay, social network. Okay. So we have, we have Facebook as a social network. We also have, Twitter as a social network. Okay. Let's try to interpret these two things. So in Facebook, what are the nodes? In Facebook, the nodes are users, right? In Facebook, users are connected to each other. And then what relation does the users are connected to each other in Facebook? On the friendship relation, right? On the friendship relation. Okay. Let's say 1 and 2 are friends in Facebook. So we create an edge between them. Let's say 2 and 4 are friends in Facebook. So we create an edge between them. And if you observe the relations here, so it's pretty, it's straightforward. There aren't any directions, right? That is, if 1 is friend of 2, then it also states that 2 is friend of 1, right? Similarly, if 2 is friend of 4, it also states that 4 is also friend of 2. There aren't any directions, or you can assume this as a bidirectional graph, okay? Bidirectional graph. But in case of Twitter, this won't be the case, right? In Twitter, you can follow node 2. Let's say 1 can follow node 2, but it's not necessary that 2 should follow back 1. Similarly, let's say 2 is following to node 4, but it's not necessary that 4 should follow back 2, right? So in the case of Twitter, we have the directed edges on the follows relation. Okay, only one of these nodes can follow each other, right? Or it can be bidirectional, right? That is, one can follow two, even two can also follow one. Okay, but directions are necessary in case of Twitter. But whereas in the case of Facebook, the directions are not required, because the friendship relation is like the both ways. It's a bidirectional. If one is friend of two, it also states that two is friend of one, right? So in case of directed, you just remember the Twitter graph. In case of undirected, just remember the Facebook graph. And we have also seen that in the case of undirected graphs, the adjacency matrices will be symmetric. Okay, the adjacency matrices will be symmetric. But this won't be the case in the directed graphs, because let's say we have the direction only from 1 to 2. Okay, in this case, how do we represent in the adjacency matrix? So we put from 1 to 2, we put 1 in this matrix. But from 2 to 1, we put as 0. Okay, because there is direction only from 1 to 2, but not from 2 to 1. Okay, so the adjacency matrices will be similar only in the case of undirected, but not in the case of directed. And there can be one other variant of graphs. Those are weighted and unweighted graphs. In this example, we don't have any values on the weights, right? We can just see that node 1 is connected to node 2 and node 2 is connected to node 4. But we are not representing any values on the edges. But in some of the graphs, we can have values on the edges. Let's say something like 100 or 200, Typically in most of the graphs, these numbers say how good these two nodes are connected to each other. That is, the numbers on the edges represent the strength of the connections in the graph. In some of the examples, we can have the weights on the graphs. So when we have the weights on the graph, so in the adjacency matrix representation, instead of keeping it as 1, we can actually represent the weight of the edge. Okay, something like 100, 200, like whatever weight that you have on the edge, you can represent that weight on the adjacency matrix instead of keeping it as 0 and 1. Okay, so we have seen the directed and undirected graphs. We have also seen the weighted and unweighted graphs. Okay, and there is also another class of graphs which are called homogeneous and heterogeneous graphs. So homogeneous, as the name says, so this is an example for the homogeneous graph, where all the nodes are of same type. Even in the case of Facebook, all the nodes are users, right? And in the case of Twitter also, all the nodes are users. All the nodes are of same type. And also all the edges are also of same type. So in the case of Facebook, all the edges represent the friendship relation. Whereas in the case of Twitter, all the edges represent the follows relation, right? So that is called homogeneous, where every node is of same type and every edge is also of same type. But it is quite opposite in the case of heterogeneous graph. Okay, I'll give you an example for the heterogeneous graph. Okay, let's consider an example on the heterogeneous graph. Okay, so here, let's consider the example of YouTube. Okay, let's consider example of YouTube. So what are all the different nodes you can have on YouTube? So you can have users as one set of nodes. And what can users do? Users can watch videos, right? So users can watch videos. Okay, I'll put it as W. And users can subscribe to the channels, right? So users can subscribe to the channels. So this is an example of the heterogeneous graph where we have three different types of nodes. Okay, we have users, we have videos, right? We also have channels. Okay, so we have three different types of nodes. And what are the relations we have? We have watched relation and we have subscription relation. So in the heterogeneous graph, the nodes can be of different types. Also, the edges can be of different types. Okay, so this is an example for the heterogeneous graph. Okay, and so that's about the heterogeneous graph. And the next variant is called multigraphs. Okay, so far we have seen what are directed and undirected graphs, and what are weighted and unweighted graphs, what are homogeneous and heterogeneous graphs. Now let's see what are multigraphs. Okay, again, to give you an example, let me give you a simple example. So let's say you have an entity called employee. Okay, you have a node called employee, and let's say you have a different node called location. Okay, and also assume that multigraphs are also heterogeneous graphs, but there is something in addition to that. Okay, let's say you have a relation between employee and location, that is employee lives in particular location. Okay, so this is one relation. But in case of multigraphs, between two pair of entities, there can be multiple relations that are possible. Okay, there can be multiple edges that are possible. Okay, so here we can say that employee lives in location. We can also say that employee works at location. Okay, we can also say that employee works at location. Okay, so between two pair of nodes or two pair of entity types, there can be two relation types. Okay, let's say employee lives in Bangalore. Let's say employee works at Chennai. Okay, so there can be multiple relations between two nodes. Okay, so that's what the multigraphs. Okay, so far we have seen all these different types of graphs. Okay, we have seen directed and undirected graphs, we have seen weighted and unweighted graphs, we have seen homogeneous and heterogeneous graphs, we have seen the multigraphs. We have also seen how can we represent the graphs using the adjacency matrices, and how can we represent the graphs using triples. And also there is one more small concept here. So in most of the cases, along with the nodes and edges, graphs can also contain some features associated with them, or some attributes associated to the nodes and edges. Okay, let's say this is the social network graph. Let's say this is the Facebook graph. Okay, this is the Facebook graph. And let's say each node represents each user. Okay, so how can we represent a user? You can just think, what information can a user have in Facebook, right? So let's say this user can have gender. Okay, and he can have location. Okay, and this user can also have number of friends. Okay, and he might also have information on like where he works at. Okay, where he works at. There can be multiple attributes informations, right? So we can represent that as a vector here, some simple d-dimensional vector. Okay, we also call this as a node vector. Okay, we also call this as a node vector. Okay, we also sometimes call it as a feature vector. Okay, so this is the meta information of the nodes. Okay, in the case of Facebook, we can represent node 1 as a feature vector which contains his age, gender, location, etc. Similarly, for every node, you can have a feature vector associated to them. Okay, and similar to the feature vectors at nodes, we can also have feature vectors at edges. Okay. In the case of weighted and unweighted graphs, we have seen that edges can contain weights, right? So weights are scalars, something like 32, 25, 46. So these are the scalars, right? But weights can also have vectors. Okay, weights can also be vectors. It can be a feature vector on the weight, sorry, on the edges. It can be a vector on this edge. There can be a different vector on the edge. Okay. So my point is, so along with the nodes and edges, graphs can also contain feature vectors at nodes, okay, and also feature vectors on edges. Okay. So these are the simple types of graphs, and what does the graph contain. Okay. And before closing this session, let me give you a simple example which we see every day. So that is the example on LinkedIn. Okay, on LinkedIn. So LinkedIn, beside every name, we see something like first, second, and third. You can just open LinkedIn and just on the feed beside every name, okay, you see some number, something like first, second, third. Okay. So what are these numbers? So this number says how many hops away that user is connected with you. Okay. Let's say you are this user U. Okay. Let's say you're directly connected to a user V. Okay. In this case, for user V, we can see it as like first because it is just one hop away from you. Okay. User V is just one hop away from you. But let's say there is one more user called W. Okay. So U is not directly connected to W. Okay. But V is connected to W. So for user U, if we see the number for W, it will show as second. Okay. Because W is 2 hops away from U. You can see W is 2 hops away from U. Okay. And if you go so on, that's what I think if it is more than 2, then LinkedIn represents as third plus. Okay. If any user is 3 hops away from you on the LinkedIn connections graph, then LinkedIn shows it as third plus. Okay. So the first, second, and third that we see on LinkedIn are nothing but the number of hops those users are away from you on the LinkedIn connections graph. Okay. Thank you.